Okay, let's get started. We must be approaching the end of the semester because I'm always forgetting something. So last class I forgot to turn on screen recording, so there's no video lecture from last Tuesday. I did, however, link to the video lecture about the Golem project and the Resilient Machines project that I taped last year. So if you're watching it and you're confused why the background looks different, that's why. Today I forgot to bring the attendance sheet, so that means you're all present today. Okay, we will soldier on as best we can here. Okay, we're working our way through this section on open problems in the field, and we're focusing on this 4-lecture segment on crossing the reality gap. How do we use the benefits of physics engines to speed up our evolutionary process, yet be able to validate our evolved solutions in physical machines? We looked at adding noise to the simulator. We looked at hooking up the simulator to a 3D printer. And last time we almost made it through lecture 17, where we were looking at the Resilient Machines project, where in the Resilient Machines project there are 2 separate evolutionary algorithms that are running throughout the lifetime of one physical robot. What are those 2 different evolutionary algorithms evolving?
One for the simulator and one for the robot.
Exactly. So in one evolutionary algorithm, we have a population of physics engines, and those physics engines are being evolved to produce accurate simulations. And the second evolutionary algorithm is evolving a population of controllers that are being run on the virtual robots inside the evolved simulators, right? And we did this by going back and forth between the physical robot and the simulated robot. Physical robot performs some random action, and it knows that when it performed this action, it gets this sensor data. It runs that first evolutionary algorithm that evolves a population of physics engines, and it's actuating, or it's running that controller it just ran on the physical machine on the virtual robot. And the fitness of this virtual robot in this physics engine is calculated how? How do we know how accurate this simulator is?
By the degree of the base?
The degree of the base. Remember that the physical robot and the simulated robot have these 2 vestibular sensors, how much the main body tilts left and right, and how much the main body tilts forward and back. How do we use that vestibular sensation to measure the accuracy?
You get a value with the real world one, and then you try to get that same exact value with the simulated one.
Exactly. So we have physical sensor data. We actuate the virtual robot, which generates virtual sensor data, and then look at the difference between these 2 sets of sensor data. The closer they are, the the more accurate that simulator must be, right? If we get a whole bunch of experiences from the physical robot and rerun them on a virtual robot, and that virtual robot generates the same sensor data as the physical robot, as far as we know, that's a pretty accurate simulator, right? So instead of actually going from the simulation to reality, we're actually going in reverse, right? We're going backwards. Once we do, and we do this back and forth a few times, get some more data from the physical robot, tune up or evolve a more accurate simulator, get some more data from the physical robot. Finally, after doing this 16 times, in this case, the physical robot said, I'm done. All of the physics engines that I have, all of the different simulators that I have all converged on this. So this must be me, right? It's inferred a model of self. We've talked a few times in this course about discriminating self and non-self. This is yet another approach to this problem. Okay, so we've sort of gone backwards from the physical robot to the simulated robot. Then, once we've done that part, phase 1, phase 2 should look more familiar. We take the best physics engine that we managed to evolve, this one, fix it, and now run the second evolutionary algorithm and evolve controllers in simulation before transferring them again to the physical robot for it to do whatever it is we want it to do. right? So two different evolutionary algorithms evolving a population of simulators and a population of controllers. And the nice thing about this is then we can keep going. If the robot's body ever changes because it becomes damaged in some way, the robot doesn't know what happened, it just knows that something has changed. So it goes back and eventually updates or evolves a new simulator that now reflects its current state, which is that it's now a 3.5-legged robot rather than a 4-legged robot. Right? Now it goes back to the second evolutionary algorithm where it's evolving controllers, and we get one that allows the injured robot to recover functionality, and it's able to move in a completely different way. The gait for this robot was very different from the one for the intact one, which makes this machine a resilient machine, which is the name of this project overall. Why resilient? Why not a robust machine? What's the difference between robustness and resiliency? Again, building blocks of intelligence. What's robustness?
Is robustness like the ability to change in different environments? Resiliency is the ability to change when the robot's body is injured.
Well, when its body is injured and it's able to carry on, that's one example of resiliency. But what's the idea of resiliency in general, or robustness in general? You hungry, remember?
I think that robust would mean that it can do very well, like perfect in every environment, and resilience would be that kind of working, but not very well.
Okay, that's one way of looking at it. So robustness means it succeeds in all environments, and resiliency is it's okay in all environments. Close, not quite what we're looking for here. So robustness is, again, the idea that you can do well in many environments, but you do well in many environments because you just sort of push through. You have a certain plan of action, you just carry it out. If it's not working, you do it faster, you do it harder, you do it stronger, you just sort of keep going, right? That's robustness. And if you're lucky, that might work, but most intelligent agents realize that that's not always the best strategy. In some environments, or in some situations like this one here, doing what you did before, faster, harder, stronger, isn't going to work. You have to stop, change your plan of action, and come up with a new plan and perform a new action to succeed in that environment. Resiliency is trickier than robustness, right? So this was one of the first machines reported in the literature that was resilient. This 3.5 robot doesn't perform the previous gait that worked for the 4-legged robot faster, harder, stronger. It realizes that its situation has changed and comes up with a new strategy. Okay, so that's what we talked about last time. I apologize for this slide, something went wrong down here. We talked about estimation. This is the first evolutionary algorithm that's evolving populations of simulators or simulated robots. Then we have exploitation down here, which is not so easy to see. This is the second evolutionary algorithm that's taking a single simulator and evolving controllers to get the robot to walk. And once we get a controller that gets the robot to walk, we transfer it to the physical robot. There is actually a third evolutionary algorithm that is also running, which we haven't talked about yet. This is the exploration point. So let me back up a little bit to slide number 9 here. This is when the robot performs a random action, gets a little bit of sensor data, starts evolving the simulator. However, it needs some more information, right? As we saw last time, it has a population of all sorts of different ones like this that match the sensor data that came back from this machine. So the robot needs to perform a new action. What action should it perform next? I didn't actually say too much about how it chose. Should the robot perform exactly the same action that it performed before? Would that be a good action to perform next? Why not?
Something's changed.
Not yet. We're still dealing with the intact robot, right? We're assuming the intact robot all it knows about itself is this. doesn't even have, it doesn't have a simulation of self yet. It performs one random action.
Oh, it's trying to collect data.
It's trying to collect data, right? So it's going back and forth, the physical robot, the virtual robot. It's performed one action. It's evolved a population of these things that are all different, and they all match the single piece of sensor data that's come back from the physical robot. So it needs more information. The physical robot needs to move again. Should it move the same way again? Forget the damage part for a moment. It's just trying to build an understanding of self.
No,
Why not?
because if not, it's going to think that that arrangement is still correct.
It's not getting any more information, right? This is still correct. It goes back to this situation. I won't bother playing all the videos here, but if you remember, it tilted about 20 degrees to the left. If it performs that action again, it's also going to tilt 20 degrees to the left, and all of those virtual description of self are going to say, yeah, we already know that. You tilt 20 degrees to the left whenever you perform that action. That was a waste of time. You just burned another experiment, another physical trial. So what should the robot do on the second time? What should the physical robot do? How should it move the second time around?
Just any other leg.
Any other leg, possibly. Remember, it doesn't actually know its legs yet. All it knows are these 9 pieces. The first action it performed was just random, right? It has no information. So it performed a random action, did a little bit of evolution. Should it perform a random action next? Would that make sense? It's not bad. Can you do better than that? Can you do better than random?
If the starfish is, if all of its legs kind of do the same thing at the same time, like by moving down, it should lean towards the broken leg.
There's no broken leg yet. Remember, it's still the intact, we still got the intact robot. All it knows is it rotated, in the first action, it rotated motor 1 and motor 5 down, and all the other 6 motors it rotated up, and it rotated 20 degrees to the left. That's all it knows so far.
Can you do a random one minus the ones you've already done?
Okay, we're getting closer, right? You probably want to leave motor 1 and motor 5 alone for a while and go explore, right? This is the exploration phase. We want to do something else. So you could do something at random, and actually random is pretty good. We've mentioned developmental psychology a few times in this course already, the study of children. If you ever watch an infant or a very young child, what are they doing? They do something called motor babbling. They're moving around, they're looking around, they're grabbing things, they're putting them in their mouths. They seem to be sort of exploring what they can possibly do, right? They're exploring the space of all possible actions, and presumably the sensory results of all those actions, right? What happens when I do this? What happens when I do that? The current thinking in the literature is that babies are just doing this at random. Just keep moving and you'll generate a lot of information. It turns out that in theory you can do something better than random, and it goes as follows. Let's imagine that we have our robot here, which in the lack of any information, the best thing you can do the first time around is random. You perform this random action, and you now evolve a whole bunch of these simulators. Remember in this little cartoon here, this is just one of them. You have a population of, in this experiment, I think we had 20 different simulators. And in each of those 20 simulators, you had a different robot, a robot that had a different body, but all of them matched the first action. All of them, when you carried out the controller on those 20 different virtual robots, all those 20 virtual robots tilted 20 degrees to the left. You can use these 20 virtual robots to decide what to do next in the following way. Let's imagine that the robot is about to carry out the same action again, this action that caused it to tilt 20 degrees to the left. If you take that controller and you plug it into the 20 virtual robots, what is that controller going to get the 20 virtual robots to do? same controller that we carried out on the physical robot the first time. If you plug that controller into these 20 virtual robots, what are the virtual robots going to do? It's the same controller, nothing's changed yet. So all the virtual robots are going to tilt 20 degrees to the left, right? They say, we know what happens with this controller. We were evolved to explain this controller. All the 20 virtual robots, they all do the same thing. The green box tilts 20 degrees to the left. They're all in agreement about that action. Let's now imagine we just choose a new controller at random, something that hasn't been carried out on the physical robot yet, and we plug that controller into each of the 20 virtual robots. What's going to happen now? It's a different controller. Are they all going to move in exactly the same way? Why not?
They're not evolved to do that.
They're not evolved to explain that one, right? So some of them are going to tilt to the left, some of them are going to tilt to the right, some of them are going to tilt forward, and some are going to tilt back, right? They're going to move differently because they all have different bodies. We have these 20 different virtual robots. They are disagreeing in their prediction about what's going to happen if you took that controller that caused those virtual robots to move differently and plugged it into the physical robot. You can think now of these virtual robots as making a prediction about what's going to happen. So virtual robot 1 says, if you put that controller on the physical robot, I predict the physical robot is going to tilt to the left. Virtual robot number 2 says, no, you're wrong. If you carry that out on the physical robot, it's going to tilt to the right. They're disagreeing. Can they all be right? If we did take that controller and carry it out on the physical robot, what's going to happen?
It's going to perform a certain action.
It's going to perform some action, right? And some of those virtual robots are going to be right or have been right, and some of them are going to have been wrong, right? Some are going to be proved right, and some are going to be proved wrong. If the first virtual robot said, I think it's going to tilt to the left, virtual robot 2 said, no, I think it's going to tilt to the right, and the physical robot actually tilts to the right, virtual robot 2 was right, and virtual robot 1 was wrong. What do you think happens if we continue evolving our population of 20 physics engines? What's going to happen to virtual robot number 1? Right? We're all comfortable with evolution, the harshness of evolutionary algorithms now. Virtual robot 1 is gone. Maybe virtual 2 survived because it's actually now explaining 2 of the results. It produces a child, and that child is similar to but slightly different from virtual robot 2, right? So now the descendants of virtual robot 2 are going to start to spread through the population for a few minutes. We pause evolution. We have a new set of 20 virtual robots. What do we do now? We know we don't have enough information. We're going to go back to the physical robot a third time. Which controller do you want to execute on the physical robot a third time? Do we want to use the first controller, the second one, a new one? A new one for sure. Which new one? We can pick them at random. You can sort of see where we're going, right? This third evolutionary algorithm also has a population of controllers. We take each controller in that third population, plug that controller into each of the 20 virtual robots. What is the fitness of that controller in this third evolutionary algorithm? What are we looking for? What kind of controller are we looking for in this third evolutionary algorithm?
One that gives you a variety of predictions.
One that gives you a variety of predictions, exactly. If we have this population of controllers in the third evolutionary algorithm, we plug it into our 20 virtual robots, and they more or less agree. You can be pretty certain what's going to happen if you download that controller onto the physical robot. So why bother, right? You're looking for one that induces maximal disagreement among the predictions of the virtual robots. Right? So we're no longer executing controllers on the physical robot at random. We're taking evolved controllers from that third evolutionary algorithm and plugging them into the physical robot in a way that we expect we're going to get the most new information out. When we plug that in, all the 20 virtual robots are disagreeing, right? So some of them are going to die when we get back the results from that new controller. Make sense? Okay. So let's put all this together now. So we have estimation up here. The physical robot is continuously evolving populations of self, right? Descriptions of self. It's using its best description of self so far to rehearse or to train controllers to do whatever NASA or the roboticist wants the physical robot to do. And it's also evolving controllers to try and extract new information. So these little green arrows here are the predictions of these 4 different models. This model says if you carry out controller I think you're going to twist about your vertical axis. This one says, no, 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 you're going to tilt this one. This one says, no, you're going to shake a little bit. This one says, no, you're going to tilt to the right. They're all in disagreement, right? So when we published this paper 10 years ago, there was some interest from developmental psychologists because up to that point, the assumption had been that when babies are motor babbling, when they are trying to learn about self and the world around them, that they're just doing it at random. But maybe not. Maybe in the baby's brain, or maybe in mammals' brains in general, we have these self models. You have an understanding of self, or you have different hypotheses. There's something 10 centimeters in front of me, or maybe it's 20 centimeters in front of me. I don't really know. I'm going to think about extending my arm. The model that says the object is 10 centimeters in front of me says I'm going to feel my hand colliding with the object. But the model that says that the object is 20 centimeters away from me says my hand won't collide with the object. So what am I going to do? The baby does this, extends its hand and sees which of the 2 models was correct. Now, whether that's what we're actually doing or not is hard to say, but at least it works for our robots. Okay, let's see. So I'm going to skip over a little bit of this in the interest of time. We will finish with the last slide here. Remember that we originally designed this experiment to cross the reality gap. So let's see how this works. I walked you through this single experiment where we went back and forth between the physical and the virtual robots 16 times. This was done before the robot became damaged. So let's put the damaged part of this experiment aside for the moment. When we did this 16 times back and forth, we got an evolved controller, and then we got an evolved simulator, and that evolved simulator was then used to evolve a controller. And that controller told us that in simulation, it believed that the robot would travel 0.5 meters, so 50 centimeters forward. Remember, the robot was trying to move from the left side of the table to the right side of the table. So the virtual robot made this prediction. The virtual robot said, I think that if the physical robot uses this controller, it will walk 50 centimeters forward along the table. We took that controller, put it in the physical robot, and the physical robot only traveled 25 centimeters forward. At least it traveled in the right direction. So again, we kind of crossed the reality gap about halfway. Didn't do exactly what the simulation predicted, but not bad. So these 2 circled points here represent the result of one experiment when we went back and forth between the physical robot and the virtual robot 16 times. We stopped, we went back, we did it again, 16 points. We got another simulator and then evolved a controller in that simulator, and it predicted this, and the physical robot actually did this, and so on and so forth. So the blue dots are the final position of the physical robot on the table, and the black dots represent the distance predicted by the virtual robot. How did we do in crossing the reality gap? So-so, right? At least the robot is moving in the right direction, right? You can see the blue points. This here represents the average position of all the blue points, and these represent error bars here. We did okay, not great. Some of them traveled pretty far. That was pretty good. The red points are showing what happens if you just take random controllers and drop them into the physical robot. The physical robot always started on the table at 0, 0, and you can see that the table might have been tilted, maybe a little bit down because the robot tended to travel a little bit forward, so there was a little bit of a bias. Could have also been because of the robot, we're not sure. But clearly there's a difference between the blue points and the red points. So this relatively involved experiment is helping us cross the reality gap. It's not perfect, but we're getting there. Okay, that's the Resilient Machines project. Any questions about that before we move on? Okay, so let's move on to the fourth and final attempt, or the fourth and final so far attempt to solve the reality gap problem called the Transferability Project. This was a work that was published in 2010, and the way we're going to do lecture 18 here and the way the paper is structured is back and forth between questions and answers. So the first question they asked in this project back in 2010 is, could you actually measure the transferability of a controller and place that measurement under evolutionary control, make it a part of the fitness function? So we haven't defined what transferability is, but intuitively speaking, how might you measure the transferability of a controller? Or what is the transferability of a controller?
How it performs in simulation versus how it performs in the physical world.
Exactly, right? So how well does a given controller get a virtual robot across the reality gap, right? If the physical robot does exactly what the virtual robot did, then that controller is perfectly transferable. If there's no resemblance between the virtual robot's movements and the physical robot's movements, no transferability, right? That's the basic idea. Hold on to that for a second. Which of course then raises this question about how to actually define it. There's one way we could do it. So before we actually go ahead and define that, we now have two different fitness objectives. One which rewards for the behavior, which as always is going to be movement. How far do you travel from your starting point? How fast can you move? That's, it's just going to be shortened to behavior throughout. The second one is going to punish for non-transferability, or reward for transferability, if you like, right? How transferable is a controller? So a controller has to exhibit two properties: get the robot to move quickly and cross the reality gap. We've got these two objectives. As we've touched on in this class before, it's tricky when you're trying to get evolution to optimize two different fitness objectives. So we're going to sort of take a digression for a moment and talk about multi-objective optimization here. So this is a very common method in evolutionary computation. It's also a common method in machine learning in general. For those of you that go out and find a job in industry doing any machine learning or any AI work at all, you will probably come across Mu or end up using Mu at some point. Okay, here we go. So how does Mu work? Well, in our case, we have two objectives: transferability and behavior. For our purposes, let's imagine we're trying to maximize these two objectives. We want controllers that are both transferable and generate desired behaviors. If we take each controller in the population and we somehow measure its transferability and its fitness, how fast it gets the robot to move, then that controller has a point in this two-dimensional space. I haven't drawn it here, but there should be a point that is at y equals 0 and x equals infinity. You can see why I haven't drawn it on here. What controller does that represent? The point that sits at y equals 0 and x equals infinity.
Still.
Stay still. right? Y equals 0 means the robot doesn't move at all. And if you transfer that to the physical robot, it's going to transfer perfectly, right? Infinite transferability. The inert virtual robot is going to do, virtual robot is also going to translate into an inert physical robot. Right? You can see there's another point up here which has a large y value and a low x value. Why do you think that's the case? Why does high I, large y, tend to equate with low x?
It's exploiting something wrong with the simulation.
Absolutely, right? So evolution finds a controller that gets the robot to explode into its constituent pieces and fly 10,000 meters forward in the simulator. If you haven't seen that yet, I guarantee you it can happen in PyroSim, right? Great. We get 10,000 meters in 10 seconds in the simulator. We transfer that to the physical robot and very low transferability, right? This is usually the case, or especially the case when you want to use multi-objective optimization, when you have two antagonistic objectives. We want to try and increase both, but usually increasing one tends to hurt the other, right? So if we draw all these points, and we took a bunch of controllers at random, let's say, and measured their transferability and behavior, and they ended up on the plane like this. Let's imagine that's the first generation in your evolutionary algorithm. Which of these survive and which die? Or which produce offspring and which die?
The outside curve.
The outside curve, right? Exactly. So we're going to draw that curve here. This curve is known in the literature as a Perrito Front. How do we actually find this outside curve? Well, you find this outside curve, or this Perrito Front, by visiting each point in the plane and labeling it as either dominated or non-dominated. So let's imagine we have visited solution S. Let's imagine we're looking at this point here, and we want to know whether it's dominated or non-dominated. We're taking S, and we're now going to look at all the other points. So here's S. We're going to visit all the other points other than S. And each time we visit another point, we're going to consider it T, and we're going to ask the following question. Does T dominate S? And how do we know if T dominates S? T dominates S if T is better or equal to S on all of the objectives we're looking at. So here's S. Let's have a look at this point up here. Let's imagine this is T. Does T dominate S? Why not?
S has better transferability.
S, as you can see, has better transferability. It's further to the right than T is. But T is better in terms of behavior than S is. T's vertical position is higher than S's vertical position. So T wins one of these battles and S wins the other one. Not dominated. We're still looking at S. Let's imagine that we visit this node now. Now this node is T. This one is still S. Does T dominate S? Yes. So T is both more transferable and produces a faster robot. It's better on all the objectives. So we label S as dominated. It's dominated by that. We color it white and we're done. We don't have to look at the other T, right? S is lost. Now imagine we visit this point. Now this point is S, and we're looking at all the other points. Are there any other points in the plane that dominate this point? Right? There aren't any points relative to this one that are up and to the right of this point. So we visited all the other points, and it never became dominated, so we labeled that point non-dominated. Did you have a question?
So with that white point on the far right,
This one?
Yeah, would that be dominated or not?
Exactly. So I realized there was a few years ago there's a typo, right? That one is actually non-dominated. So you're right. This one should actually be black because if you look at this one here, there are no other points that are up and to the right. Good catch. You're right. So the Perrito Front should actually be drawn here. You got it. Okay, so we found the Perrito Front, where we found the solutions that are non-dominated and dominated. Which solutions die and which ones survive?
The non-dominated survive.
The non-dominated survive and the dominated die out. The survivors, the non-dominated solutions, get the privilege of producing offspring. Let's imagine that this one here produces an offspring, and that offspring lands here in the plane because it obtained this transferability and this behavior. What happens now? Who lives and who dies?
The parent dies.
Unfortunately, the parent dies because it's dominated by the child, right? Evolution is cruel sometimes. Okay, what's going to happen as we continue running this multi-objective optimization method? As the generations start to elapse in evolutionary time, what's going to happen to this picture?
Probably a lot of black dots.
Possibly. So this is an interesting question. Do the number of black dots increase or decrease? For two objectives, usually there's not that much change.
I feel like it would turn into the first quadrant of the 0 or 2 equals the square root of x squared plus y. It'd look like a circle. It'd be the top right of a circle to where it rounds out. So
Top right of a circle, you mean you're going to get something like this?
yes.
Okay, that's what you would like to have happen, right? It depends on how antagonistic the two objectives are, right? Hard to say. Can we say, that would be nice, right? But that's probably not what's going to happen. What's going to happen in general?
It's just going to keep shifting.
It's going to keep shifting in which direction? Up and to the right? So that's why it's called a front, right? It's like an army's front in a war. It's pushing forward. In this case, it's pushing up and up to the right. We're trying to find solutions up here that are both very transferable and produce fast robots. If we get a convex curve, right, that would be lovely. Maybe we don't, but at least we get stuff that starts to land up here.
Although the convex curve would look nice, wouldn't it be ideal if you just had a point at the top right of the graph? Wouldn't that be like the ideal point?
That would be the ideal point, right? And that is what we are trying to do, is find that theoretical optimum which is maximally transferable and produces a fast virtual and physical robot. Probably in reality it doesn't exist. We don't know how far up and to the right we can get. That's the game we're trying to play here.
And can you determine the ideal, what are the points called again? Non-dominated point? The ideal non-dominated point just by its distance from the origin?
The ideal one, again, has infinite transferability and infinite speed.
The best one among the stat we have.
Okay, a good question, right? So in the Perrito Front here, we have multiple solutions. Among the non-dominated solutions, which one is the best? I think that's what you're asking, right? That is the million-dollar question. There are thousands of papers that have been published in the Mu literature about, maybe not thousands, hundreds of papers about how to really, once you have the front, which one is really the best on it? The theoretical answer is there is no way. So all of these solutions are known to be Perrito optimal. If you look at all of those black dots and you compare those black dots against each other, it's apples and oranges. One is more transferable, one produces a faster robot, right? You could, of course, take the distance of those black points from the origin, 0, 0, and just decide that that's how you're going to measure the best one. There's lots of other ways to do it. We don't have time in this lecture to get in it, but if you research multi-objective optimization, you can see, you dig into the literature and there's lots of solutions to this problem. Okay, again, I wanted to spend some time on this because again, in your final project, you might want to use this approach. You might want to produce a quadruped that moves very quickly, but doesn't fall over, right? So you could do exactly the same thing where you have speed as one of your objectives and stability as another one of your objectives, right? Then you got to think about how to measure stability. How would you use the quadruped sensors to detect when or whether it falls over? Okay, common technique, you can give that a try if you like. Okay, so again, you have my little cartoon here. You can sort of see eventually you would march to the up and to the right. Okay, here's some data from the actual experiment. So we have speed on the vertical axis here. The horizontal axis is flipped. So they're actually trying to maximize speed and minimize simulation to reality disparity. Usually I like to try and either maximize all my objectives or minimize all my objectives just because it makes it easier to sort of parse. But here they're trying to maximize this objective and minimize this objective, which means optimization is pushing up and to the left. Right? They took this snapshot partway through an evolutionary run. So the x's represent, that's right. The x's represent the controllers at generation I, so the previous generation, and the current generation in this picture is I plus 1. And sure enough, if you look very carefully, you can see the black dots represent the Perrito Front here. We're pushing up and to the left. And the white dots are all the dominated controllers that lie behind the front. Okay. You'll notice on the horizontal axis here, they're mentioning approximated disparity. What this means is before they've even transferred these controllers to the physical robot, they're able to make a guess or an approximation for how transferable they are before they've transferred them to reality. We haven't talked about how to do that yet. We'll come back to that in a moment. They took all of these controllers and actually ran them on the physical robot. And so now they know the exact disparity. So remember, we're trying to minimize disparity. We can see some of these points move a little bit because their approximate disparity is not the same as their exact disparity. Okay, we'll come back to that in a moment, but I just wanted to show you what a real Perrito Front looks like in their experiment, at least. Okay, so let's come back to our questions and solutions here. We're trying to optimize controllers against transferability and speed. The problem here, if we're going to do transferability, as far as we know at the moment, the best way to measure transferability is transfer the controller. But if you do, now you have to evaluate every controller on the physical robot. Why are we even bothering with simulation at all, right? Might as well just throw it away. So this doesn't really help us very much if we want to try and use simulation. So can we do something else? Can we predict transferability before we've transferred something to reality? That's what we're going to see next. Okay, I'm going to walk you through this. Let's imagine we have this sample experiment here where we have a whole bunch of random controllers. None of them have been transferred to reality yet. We just generate some random controllers. We carry them out. We execute them on the virtual robot, which means they all fall on a line here. I think you can see the dots here, right? We don't know how transferable they are. So all we have is these points where the height of the point represents the speed of the virtual robot using that controller. Okay, which of these controllers do you want to send to the physical robot? The one at the top, right? Maybe you get lucky. The controller that makes the virtual robot move the furthest or the fastest. Maybe it will transfer. You don't know, right? So let's take that one, which is exactly what they did, and we're going to run it on the physical robot. So let's have a look at the virtual robot first. You thought it was going to walk forward, right? Looks pretty good. You'll notice the robot they used here is actually a wegged robot. So a wegged robot has legs, and at the bottom of the legs are wheels. At the moment, they've locked the wheels, so we've got a standard four-legged robot. Let's see if I can find the Okay, so they took that single controller and transferred it to the physical robot, and they got this. How do we do? We fell into the reality gap, right? Didn't work. Okay. So we know that that point up there has low transferability. So now we've tagged that point with transferability. We could continue evolving the controllers, but let's imagine that you're going to pick another controller in this population now and transfer it to the physical robot. Which one should you transfer?
The next best one.
The next best one? Is that the best thing to do? You're an optimist. Why might you not want to transfer the next top one in the list here?
I mean, if they're antagonistic, maybe getting the lowest one with highest transferability.
Maybe. Okay, so we have a pessimist now, right? Take the worst one that at least is doing something. It's non-zero, and see if at least that will transfer to reality. We could do that, right? The intuition for what we're actually going to do is say, yes, we probably don't want to transfer this one up here because it's probably similar to the one that we just transferred, right? So if they're close in terms of speed, maybe that's not such a good idea, right? We could, of course, be pessimistic and take the smallest one. Maybe we should kind of hedge our bets. We want to pick something that's relatively high in terms of behavior, but is also quite different from the one we transferred before. That's the sort of intuition we're going to use here, which is the one that we're going to transfer is the one that is as different as possible from the one that we've transferred before. So let's walk through this now. So the solution to this problem, that we would have to transfer every controller, is we're going to try and estimate the transferability of a controller before we set it to reality based on its similarity to other controllers that we have sent to reality. We're going to have a growing set of controllers that have been executed on the physical robot, and we know their transferability. Okay. Every solution raises another problem. How do we measure the similarity between two behaviors produced by two different controllers? Could use speed, that's one. How else might we do it? Distance traveled. Okay, if we evaluate our robots for a fixed period, that equates to speed. Given all the videos that I've shown you so far in this reality gap segment of the course, what sorts of properties of the behavior look like they're going to have an impact on whether it transfers well or not?
Whether it's taking advantage of the simulator?
Whether it's taking advantage of the simulator, exactly, but we don't know that because we haven't sent anything, or we don't know exactly what's happening. All we can do is sort of measure the behavior of the virtual robot and measure the behavior of the physical robot. Are there properties of that behavior that might signal it's not going to transfer well?
The gait, maybe?
What's that?
The gait of the robot?
The gait, we're getting closer, right? So what sorts of gaits are unlikely to transfer well? Lots of friction, right? Things that are high friction, things that are banging, sort of very exaggerated movements, maybe sort of things like that are not really what we want. We don't really know, right? So we would like to not make too many assumptions. So what the investigators did was to define behavior as B, a vector, and this vector has 3 elements in it, and these 3 elements describe 3 different properties of the behavior B produced by a controller C. We take C, we drop it onto our robot, the robot does its thing, it produces its gait, and we watch that gait, we observe that gait, and measure 3 features of that behavior, F1, F2, and F3, and we're going to use that to measure similarity in a moment. First one, as we already said, is distance, right? How far and how fast the robot moves is probably going to be an important aspect of how transferable something is. We're going to look at, or the investigators looked at mean height of the robot during travel. So if it was doing this or sliding across the ground, they're going to measure that mean height, which is maybe a way to get at friction or other aspects of the way it moves. And they threw in final orientation of the robot. Which angle was the robot pointing at the end? They just put it in there hoping it would be helpful.
Is the mean height normalized at all for the height of the robot itself?
I don't know. I doubt it is, because they're going to be comparing these B vectors against other B vectors, right? It's all for the same robot. So probably not, but I'm not sure. Okay, so now we have two controllers, C1 and C2. We can now measure the distance between them, or the similarity between them, if you like, by just taking the Euclidean distance between the behavioral vectors produced by C1 and C2. What happens if we take these two controllers and behavioral distance equals 0? What does that mean?
Has the ideal transferability?
What's that?
Is that the ideal transferability?
Oh, we're talking about distance here. We're not talking about transferability yet, right? All we're looking at is two different controllers. They produce two different behavior vectors, and we compute the Euclidean distance between these two B vectors, and it's 0.
They do the same thing.
They do exactly, well, they don't necessarily do the same thing.
Their behaviors evaluate the same.
The behaviors evaluate the same way. They travel exactly the same distance. Their mean height is exactly equal. And the final orientation is also equal. Yes, they probably did exactly the same thing. We know by definition here that if we plugged in C1 and C1, it would produce, again, let's assume there's no noise, there's nothing else affecting the behavior of the robot. Robot will do exactly the same thing twice, and we will get a behavioral distance of 0. If behavioral distance here is far from 0, it's a very positive value, what does that tell you about the behaviors produced by C1 and C2?
They're just totally different.
They're totally different. One moved slowly, one moved fast, one walked on its tippy toes, one crawled along the ground. One ended up facing forward, the other ended up facing backward, right? Very, very different behaviors. Okay, so now we've got this distance measure between two controllers. We're going to use it now to define transferability. How do you think we're going to use it to measure transferability?
If there's similar, you can just test one, and then everyone that has a similar enough distance or whatever, you can just say has the same transferability.
Exactly, right? So we're going to look for controllers that are far from controllers that have been transferred to reality so far. So we're going to define transferability of controller I here. So we're considering, we've evaluated CI on the virtual robot, but we haven't sent it to the physical robot yet. We're considering sending it, but we would like to try and predict its transferability first. If we predict that it's not going to transfer well, then let's go find another CI and try and transfer that one. So the transferability is going to be measured as the negative of the distance between CI and CSI and CRI. Or sorry, this is actual transferability. Let's assume my fault. We took CI, we ran it on the virtual robot, and we ran it on the physical robot. How transferable was it? We take the distance between the behavior produced in simulation and the behavior produced in reality. If CSI and CRI, the distance between BSI and BRI is 0, that means that the physical robot did exactly the same thing as the virtual robot using controller CI. Very high transferability, right? That's why we have the negative here. So if we get a 0 over here, that's the best you can do, right? That's maximum transferability. The more negative this value is, the greater the gap in behavior between the simulated robot and the physical robot. So a transferability of -100 says this controller doesn't transfer well from simulation to reality. So far, so good? Okay, but this is still exact transferability, right? We want to try and predict the transferability of a controller before we send it to reality. Okay, how do we do that? Well, we'll take this equation a piece at a time. We're going to estimate the transferability of controller C using this equation here. We're going to assume that we have a growing set of already transferred controllers. So CT here is a set of controllers that we have sent from simulation to reality. We're going to take, let's work on the second term here for a moment. We're going to pull controllers out of this bag, CT, one at a time. Every time we pull a controller out, we call it CI. And we know the transferability of CI because we've already sent CI from simulation to reality. So we know its transferability. We divide it by the distance between CI and C. Why do we do that? And we keep summing them up. So we pull another CI out of the bag. We know the transferability of CI, and we divide by the distance between CI and C. Maybe there's one more detail here that's useful. The distance between C and CI is the distance according to the simulated robot, because C has not yet been sent to the physical robot. All we have is behavioral data from the virtual robot using C, and we have virtual data from the virtual robot using CI, so we can measure this distance. We're summing up these transferabilities over all of the controllers that have been sent to reality and dividing by their distance from the one we're trying to estimate, C. Why divide by this?
If the B distance is closer, so if they behave similarly, is that a high value or?
Exactly.
So if it's a high value, then it's going to decrease the negative value of the transferability. So they would say it's more transferable.
Exactly, right? So if the distance, actually let's flip it around. Let's imagine that CI is far from C. It does something very different. We're dividing by a big number, which means we're pulling this towards 0. We're reducing the influence of this component of the sum on our estimate. Maybe we pull out another CI from the CT bag, and that CI is very close to C. So if it's close to C, we're dividing by a very small number, which magnifies this number. So we're actually computing here as a weighted sum. And we're looking at the influence of each of these CIs on C. Which CIs have a greater influence on C than others? What's that?
The largest one.
The largest one, the ones that are closer to C, right? So if I'm C and we're trying to measure my transferability, and there's another CI right here, which is very close to me, it produces similar motion than me, then we just look at its transferability, and that's my transferability, right? We're using CI as a proxy for C. But another CI, which is distant from C, they're very different. I'm going to discount. I'm dividing by a big number. I'm discounting that controller's transferability or lack of it, right? I don't care. We're basically saying the transferability of C is sort of the average of all the transferabilities that have been measured so far, but weighted by the distance. This term in front, you can see, is also summing over CT, but now it's the distance is in the numerator. Over here, it's in the denominator. So this is just normalizing this whole thing. So this isn't really too important. This is just a normalization term. Right? So if there's a bunch of CIs close to C, we're sort of looking at all those close CIs, and however transferability they were on average, that's our prediction for C's transferability. Right? We're discounting transferabilities of controllers that are far from C. Make sense? Okay, so that's what we're going to do now. We're going to use that. So we can now take all of the controllers that are in the population that have not yet been sent to the physical robot, and we can use this to compute or estimate their transferability. So we make predictions. That one's transferable, that one's not so transferable. Which one do we send to reality next? We have a whole bunch of them that we've evaluated on the virtual robot. We know how fast they make the virtual robot move. We've estimated their transferability, how likely that speed is to translate to the physical robot. Which one do we send next? Let me go back to this picture, which maybe helps ground your intuition. So imagine now that all of these points have spread out along the horizontal axis. We now have a cloud of points again. Which one do we send?
The one with the highest predicted transferability.
Okay, another optimist, right? The one with the highest transferability. Also the one that gets the robot to move fast or move slow, or just transferability in general.
Well, those equations we just worked on were to predict how high it was going to be, right?
These are used to estimate transferability, which is the horizontal axis in the little cartoon here. Right? We know the height of the points because we've evaluated them on the virtual robot, so we know how fast they get the virtual robot to move. Which one do we send to the physical robot next?
I would think it would be the one that we've estimated to be the highest.
To have the highest transferability? I will imagine that in most cases in reality it's going to be one that is down here, right? Slow-moving robots are going to be estimated to have high transferability, assuming we've already sent some slow robots across. Let's assume that our estimated transferability is pretty good, right? So we don't necessarily just want to send controllers across that have high transferability because, again, we could send across ones that are producing slow-moving robots, which is not really what we want. We also don't want to go to the other extreme and send the ones that have high behavior because they're probably going to be estimated to have low transferability. So what do we do here? Do you have an idea?
Maybe choose the estimated transferabilities that we don't know are that accurate.
Exactly, right? So remember back half an hour ago to the Resilient Machines project. What did the Resilient Machine project do? It tried to do something new, right? Something where its internal model said, we don't know what's going to happen. You're going to tilt to the left, maybe you're going to tilt to the right. Not so sure, right? Similar principle here. We're actually going to, let's see, where did we get to? Which controller to try in reality next? We're going to send across the one that's most different from all the ones that we've sent so far. Okay, last equation of the day. Here we go. Okay, we're going to send a controller that is most different from those in the population. So from those in the population of those that have been already transferred, right? We've sent a bunch of things across. The next thing we send across, we would like it to be as different from all the other ones we've sent across so far. How do we know that it's different? Well, luckily, we've already defined this distance metric, so we can just reuse it. If we're thinking about the diversity of C, how different is C from all the other CIs in the set CT that we've sent across already? We take the distance between C and each CI, and we take the minimum then of all those distances. Why the minimum? We're going to define the diversity or the uniqueness, if you like, of C as the minimum of its distance to all the other, the minimum of all of the distances to the other CIs that we've sent to the physical robot. Why the minimum?
We want the one that's furthest away from the closest.
The one that's furthest away from its closest, right? So I'm just going to do this in one dimension for you. Let's imagine we have C here, and the other CIs, I'll just do C prime. The other CIs are out here, so it's starting to look like C is pretty diverse, but it turns out there's another one here that we've already sent to reality, right? This is the minimum distance here. We don't want to send that one across, right? We already know quite a bit about this behavior. This one is likely to produce very similar behavior. Don't bother, right? We're looking for some other C in the population. Actually, let's leave our C primes here, because these are the ones we've already transferred across. Turns out there's another C in your population that's sitting here. It's pretty far from its closest neighbor. Its minimum is pretty high. That's the one we'll send across. Right? Okay, so we're always sending across the most diverse one. When we do, we get information back, and we keep going. We play the moo game here, where we're trying to move this front up and to the left. We're looking for controllers that produce fast robots and have low SDR disparity, right? We're looking for things up here, and it's sort of these points up here that are likely to do what we want. Give us a fast virtual robot, and, because they're up here, to the left, they're likely to have low disparity. They're likely to also produce a fast physical robot. So far, so good? So like the Resilient Machines project, they went back and forth a few times. They started with a random controller, produced fast virtual robot, slow physical robot, so high behavior, low transferability. They estimated new ones. They evolved for a while, pushed the front up and to the left, picked a new one based on this, sent it to the physical robot, got a new piece of data, put it into the CT bag, the controllers that had already been transferred, went back and pushed this front up and to the left again, back and forth a few times, until they got, after a few times, this. And here we go. Okay, so so far in this lecture, I've only shown you one controller. I showed you it on the virtual robot and then the physical robot, and that controller fell into the reality gap, right? You can bet what's going to happen in the second and last controller I'm going to show you for the day. If I can find it. Here we go. Here it is in simulation. How does it compare to the first controller I showed you, if you remember?
Not as far distance.
Not as far, but not bad.
Very similar motion.
Very similar motion. Okay. Here we go. Here's that second controller now transferred to the physical robot. How did it do? We made it. We made it across the gap. It took 20 years or so to do it, but we're starting to get there now, right? Okay, we've only got 4 minutes left, so what I'm going to try and do, if I can, I'm going to show you all 4 videos together. I'm going to try. Let's see. And I'll try and line these up here. So the first controller that was sent across the gap is on the left here, and the second controller that was sent across the gap is on the right. We're going to play the spot the difference game. Let me move these up a little bit for those of you in the back. Let's play spot the difference game between these two controllers. Okay, here we go. Why did the first controller fail and the second one succeed?
The second one lifted its legs up higher when it was pulling itself over, so it was allowed to move more.
The second one pulled up its legs more?
Yeah, that first joined in. Yeah, it looks like it kind of pulls up more, so it's allowing it to push off and get more distance.
Maybe. Other observations?
Second one is holding its body higher off the ground.
Think its body is a little bit higher off the ground? Possibly. Other observations?
The second one is rocking back and forth.
Second one is rocking back and forth a little bit. More or less? More? More? I know the authors of this paper quite well. Every time I see them at a conference, I always pester them. What was the difference? They have no idea why one transferred and why one didn't, right? At least visually, they look almost identical, right? This is sort of the maddening thing about the reality gap. Whatever this controller is exploiting in simulation, who knows what it is or why it did it or how it did it, and this one, because of the work of this algorithm, managed to avoid whatever those exploitations were. Impossible to say, right? If we built another robot and placed it in a different environment, there would be other aspects of the physics and the environment that evolution would try and exploit. We can't, in my opinion, we can't try and a priori predict what all these exploitations are going to be. We just need to have one of these processes, one of these algorithms that automatically works to cross the gap. Did you have a question?
Yeah, I agree that the second one rocks a bit more, but
Yep.
I would think that the result of that in the real world would be that more of the robot's weight is put on the wheels, which would give it more traction.
Possibly, yeah, that's right. So it may actually be that it's somehow trying to minimize, like we talked about before, minimize the difference in friction, right? If the friction in the virtual ground and the physical ground is very different, then you should sort of push down mostly vertically and try and put most of your weight on that foot, right? Don't slide it forward and back. We're all Vermonters by now. You know when you walk on ice, that's exactly what you do, right? Most of the force in your footfall is vertical rather than diagonal. Maybe that's what's going on here. It's hard to say. Okay, we will leave the reality gap, and on Tuesday we will address scalability and crowdsourcing. You have a quiz due tonight, and you're working on your first deliverable. Thank you.